Okay, today we are going to be treating surface tension, vaporization, and boiling point. The idea of this class is to just make you understand what it's talking about. It's not like we're doing calculation, but just for you to understand the concepts. So, when I hear surface tension, let's say this is a containing vessel, and inside this containing vessel, I have a solvent. You can call it water, it can be anything, and I have the molecules of this solvent scattered all over. Let's say this is the molecule of the solvent scattered everywhere inside this container. So this, let's say this is water. It can be any solvent. So scattered all over. What we are saying in surface tension is that as this molecule is scattered all over, every solvent has intermolecular forces. So far as it's not ideal solution, it has intermolecular forces. All these arrow you're seeing is like the intermolecular forces holding it together from the other one. Like that is their attraction to the other one. So as they jump up, they tend to collide, see if they can hold each other together. So this is the attraction forces. We are using this to establish or to show the attraction forces. Now, the concept here is that these water molecules, the ones up, has should I say, it acts as if it is a covering, such that if an insect comes, it can perch on this, stay on top of it. Even if you take light something, let's say broom, for example, broomstick, put on top, you see that long as it's not very heavy, it will float on top of it. So by that understanding, it simply means that the ones that settled below, they don't have enough kinetic energy. So the ones that are above, because when it has more kinetic energy, it's able to move up and stay on top. And this particular behavior that exists in water molecules, we say that there's an inward force acting on it. That this inward force that is acting on this water liquid, that wants it to break free from the surface, or should I say, or we normally say that an inward force that needs to be overcome. Better, there's an inward force that needs to, there's all this force of attraction. So there's an inward force that needs to be overcome, which is this force of attractions between them, so that we can break free from the surface of this liquid. And this is what happens when the water gets heated. So if I apply heat now, I apply heat, the ones down will tend to move up. They tend to move up. The ones up will come down. And as it receives the heat, it will tend to move up. Those ones that moved up will move down. This is what will be happening. And as it happens, at a point will be reached. Because naturally, as this thing is happening, when you heat your water, for example, it doesn't start boiling. Rather, there is a pressure on it naturally that holds it back from exhibiting that boiling. But as it gets heated at a point, it will get equal to the environmental or external pressures, so that you now start to see the movements, or now start to see what is happening inside it. It breaks free. So we say that this inward force has been overcome. So that inward force that needs to be overcome, that's what we call surface tension. So we say that surface tension is defined as a measure of the inward force that must be overcome in order to expand the surface of a liquid. So we say that it's too much. So we say that surface tension is defined as a measure of the inward force that must be overcome is defined as a measure of the inward force that must be overcome in order to expand the surface area of a liquid. So we normally give this surface area as force over length. I would say it's the ratio of force to length. So that surface tension. So we can also define it as the force in Newton temperature acting parallel to the line on the liquid surface. So it is temperature dependent, and surface tension decreases with increase in temperature. So as you notice, as we applied heat, those forces of attraction tends to get decreased, so that this surface can be expanded. So that's for surface tension. So when it is when we say boiling point, it means the time to get a temperature that meets the atmospheric pressure. So if we say that something has a high boiling point, it means that it has a high surface tension. Understand? So measure of the inward force that must be overcome in order to expand the surface area of the liquid surface, the tension on the surface. So tension on the surface is a measure when it's tensed. However, I'm trying to think of things that you use in remembering it. So the next one is what we call vaporization. First, I like to explain vaporization first from the concept of evaporation. We know that it simply means liquid changing to gas, and we've heard of volatile before. If a liquid or a solvent readily changes to vapor or readily evaporates, we say it's volatile, and if it doesn't evaporate, or should I say, if it doesn't evaporate easily, we say it's non-volatile. So if I know this concept, what it means is that as liquid gets heated, for example, let's say this is water, let's say this is the molecules. As this gets heated, this water molecules, as it gets heated, we know that it has forces of attraction. As it gets heated, what we can notice is that if it is not covered, it will get heated, can even boil, then evaporate, and there will be nothing left. But once there is a container, once this is covered and is getting heated, what we notice is that at a point the vapor will be held here, it will be trapped here. On top of all these places, it will be trapped. So what will happen is that at a point, it will get to a point where the vapor that is trapped on this cover above will now start to return back as water. In that case, we say it's condensation. So as it's returning back, we say we've established a point of equilibrium. At this point of equilibrium, we say that we have what we call any more heat applied, we say that it has gotten enough heat. So there is pressure exerted on top of this place, on top of this water, above this water. And as you're applying more heat, that vapor is, or should I say, receiving more pressure. We say that is vapor pressure. So as you heat it more, when it has reached that point of equilibrium where it goes up and condense, we say that that point it has reached what we call saturated vapor pressure. And this saturated vapor pressure is independent of the amount of liquid, so it must occur. And when this saturated vapor pressure gets to a point where the external pressures, that is atmosphere, the pressures due to the atmosphere that was entering the liquid, or that is keeping it from, should I say, the vapor leaving, going into gaseous state, when it equals to that point where the atmospheric pressure can no longer hold it back, when they get equal, that is when it gets equal to atm, atmospheric pressure, what we experienced at that point is now boiling. So we say that boiling points or boiling, we say that boiling point or boiling is simply that point where saturated vapor pressure, that, or we say it is that temperature, because all these things are happening at a temperature. Notice that heat is applied now. So that temperature where saturated vapor pressure is equal to atmospheric vapor pressure is what we call boiling point. So if I know this, I can say that I can define boiling point as the point at which, should I say boiling point, I can define it as the temperature at which vapor pressure is just equal to applied pressure. So I can say it is boiling point. I can say that boiling point is the temperature at which vapor pressure is just equal or is equal to applied pressure. And this applied pressure, we know that is like, should I say, whatever I'm heating, there is pressure applied to it, and as it gets to the point where the pressure becomes equal to the atmospheric pressure, we can now see that boiling point will take place. That is why for normal level, water has a vapor pressure, or yes, a vapor pressure of 760 millimeter mercury, and this vapor pressure happens at 100 degrees C. So when the applied temperature, or when the temperature gets to that point where it becomes 100 degrees C, we can say that it attains 760 millimeter mercury as its vapor pressure. At this point, the applied pressure, that is the atmospheric pressure on that water, can no longer hold it back. So it starts to experience what we call boiling point. So water boils at 100 degrees C. So it gets a 760 millimeter mercury vapor pressure at 100 degrees C. So that is all I want you to know for right now about surface tension, vaporization, and boiling point. So in vaporization, I can simply tell you that the idea of vaporization is that tendency that liquids or solvents have to change from liquid state to gaseous state. So before I round up, I want to talk about saturation. This saturation. So we say that saturation is defined. Saturation is defined as that point whereby the solution can no longer, or the solution can no longer take more solutes. I will say a solute can no longer be added. That point whereby a solute can no longer be added to a solvent and it will dissolve. So at the maximum point whereby enough solute cannot cause, or addition of solute cannot cause the solution in the solvent, or cannot be dissolved in the solvent, we take it to mean saturation. And another one I normally explain to students is precipitation. When you hear precipitation, you're thinking about, does the solid or whatever solute you have, does it settle, does it go and settle under the liquid? So if it doesn't settle, you say no precipitation. If it settles, that means precipitation occurs. So that is for now what I want you to understand about surface tension, vaporization, and boiling points, so that we can move over. Our next class will treat ideal solution and mixtures.